Thanks for clicking this lecture video regarding the 6.5 reflectivity and transmissivity of an interface. And essentially what I will be doing here in this lecture is that I will generalize what we have learned regarding Fresnel coefficients and understanding of field transmission and reflection at an interface between two dielectric media regarding the field amplitudes. I will now generalize these concepts to irradiances. So really into the, in a way, intensity of light propagating through the interface or being reflected. So, as I already mentioned, Fresnel coefficients, as we so nicely learned in the previous lecture, they apply for the field amplitudes. So please recall the defining equations we were operating on EIs, ERs, and ETs. So that would be the field amplitude quantities. And the trouble here is that they don't really exactly or explicitly describe how much of optical energy actually is being reflected or transmitted through the interface. So, okay, of course, they do give us the amplitudes, and of course, we could calculate from the amplitudes what is the irradiance of reflected light, but it's not explicitly visible in this framework of using just Fresnel coefficients, but rather they are operating on amplitudes. And here we do this generalization, and essentially we will now use a treatment or introduce to you a treatment where we can understand how much of field energy is actually being either reflected or transmitted. And in here, the essential concept and parameter to describe things with is the irradiance. And here I will start as before, but now since we actually do need to consider a given amount of energy and not just energy density, I will need to adjust things a little bit. I will still come with a plane wave like quantity into an interface, and the incidence angle still is theta I. But now actually instead of coming with the plane wave, I need to imagine that I'm coming with for example, a given sized beam or only like a portion of the plane wave. And the cross-sectional area of this portion of a plane wave or my beam will be denoted with A. And this beam, I will just use a terminology of beam here, but you could equally well just imagine that it's a portion of a plane wave. It's now incident on the interface. And here here is the cross-sectional area into which, or cross-sectional area which I'm illuminating at the interface with my incident beam. And the other parameters will be essentially the same, but the change is in the fact that now we are considering a specific area so that we can actually calculate how much of energy or irradiance actually is being incident on the interface or being reflected and so forth. And of course, we can start by just writing the equation we know for the irradiance. So I, irradiance. And most of the time, optics people equate irradiance with intensity. And this is especially so when we are speaking about things. I'm also most of the time using of intensity. But pedantically speaking, of course, I should say it's irradiance because intensity is defined slightly differently. So there's also the kind of directional angle involved in definition of intensities, depending on the kind of context. So irradiance I, and most of the time you could just say intensity or power density. That would essentially also be the same thing, but let's use term irradiance for the sake of clarity here. So intensity equals irradiance is defined as 1/2 times the refractive index times the speed of light times epsilon 0, that's the vacuum permittivity, times the modulus square of E0, that's the field amplitude. And please note here that we have the refractive index in there in the equation for the irradiance. This is actually important. So the irradiance changes when we go into a different medium. The reflectivity, capital R, of the interface, also known as the reflectance, is defined as a similar ratio between the incident and reflected powers. Or, this is actually a power because we are multiplying intensity with the cross-sectional area here. So, similar to the small r, the Fresnel coefficient for reflection, we can now define reflectivity, capital R, and we define it as a ratio of how much of but power is incident on this area. So that would be the IR times A times cosine of theta R divided, how much of power is being reflected divided with how much of power is being incident into this given plane of interest. So here, essentially, I have my intensity or irradiance of the incident beam, II, and then I have my cross-sectional area, A times cosine of theta I. So essentially, I'm taking of this, and this still tells me of the power of how much of light is incident here. So essentially of how much of energy per unit interval of time is incident in this area of A at the interface. And then here on the numerator, I have the reflected intensity IR times A times cosine of theta R. So essentially I'm just looking at of how much of power is going through this kind of cross-sectional area of this guy here. And then this is essentially the same way as we would define a Fresnel coefficient for reflection, but now we do the same thing for a reflected powers so that we can actually describe things a little bit better in terms of irradiance. We can plug in the values. So essentially the A's and cosines vanish. So what's left are the irradiances. And now we can plug in from the equation above for the irradiance. And we get equations that we have Ni times C epsilon naught divided by 2 times the modulus square of reflected field amplitude. And then on the denominator, we have the same kind of quantities because we are at the same medium of I. Now what we're left is that there we have the square modulus of Fresnel coefficient R, and that's our reflectivity. So this is actually quite nice, so that the generalization is intuitively very easy to understand, so that they basically just take the Fresnel coefficient for reflection R, and since we are using amplitudes to define that, we just modulo square this quantity, and then we get into the irradiances. So in a way, it kind of resembles this kind of behavior there, that we have the field amplitude modulo squared, and that gives me proportionality to the irradiance. And this definition also, we can easily apply that for a lossy media. And that means that we would have a complex valued reflection coefficient. And mathematically, that would state that the R is a complex number since we have the modulo square there. So we could also just extend our situation to a case that there will be some losses, absorption, and that would affect also the reflectivity. And similarly, like if you would have a complex valued Fresnel coefficient, that would also imply that there will be some additional phase change in the reflection process, and these actually do happen. Recall in the future, for example, behavior of fibers and waveguides, and the kind of how do we understand their behavior, performance. Then here, if you plug in a complex valued number here, there would be an additional phase change in the reflection. But when we're actually measuring irradiances, and we are looking at the capital R, the reflectivity, the phase change doesn't really change the irradiance, but rather the irradiance will be constant valued. So of course, this is nice. It kind of complies with our basic understanding of how things should work. And next, we will do the same thing, but now for a transmissivity or transmittance. And this is the capital T. And here, we essentially define it as a similar kind of power ratio between the transmitted and the incident fields. So the capital T, essentially we also define it that it's the IT times A times cosine of theta T divided with the incident power. So we have the theta I times A times cosine of theta I, and in the denominator. So essentially here, what we have the transmitted energy, transmitted power, better to say transmitted power because that's the quantity, not energy. So energy per unit interval. And so we have the cross-sectional area of A times cosine of theta T. And then theta T is the refraction angle. And then we have the transmitted irradiance, IT. And then we have the incident field and the similar power quantities given with the II, A, cosine of theta I. We plug in the equations, and surprisingly, what we get out perhaps is that now the refractive indices and the cosines of theta T's and theta I's do not vanish from the math, and we are still left with the modulo square of the transmission coefficient Fresnel coefficient. And here we actually do see that something actually changes because we are going into a different media. So that we are left with this kind of additional term in the transmittance, capital T. And here it's really important to note that the T here is not just directly proportional to the modular square of the transmission coefficient, T squared. So that this is actually something to note and remember. And this is only arising from the fact that we have two optically different materials and they have different refractive index profiles. So essentially, they recall the equation for the irradiance I, so that we had the dependence on the refractive index there. And then on addition, we're defining things such that we have a kind of same amount of power in here at the interface, so that then we also need to have these cosine terms for the angle here. Here, I do not show this, but one could show this via a direct calculation, that if we would take the reflectance R and the transmittance T, they would fulfill a simple equation that R plus T equals 1. And this would be the case especially when we happen to have flat interfaces in optical point of view. So essentially optically flat surfaces where the surface smoothness would be way better. It would be way smoother than the order of the wavelength. So that then essentially all light would be reflected nicely and transmitted, and there would be no scattering at the interface. And then this equation would be applying here. So that this is the kind of limitation of this condition. But if we would have a rough surface and there would have a kind of surface scattering induced losses, then we should introduce, for example, let's say like a capital S parameter here that would describe us of how much of energy is being lost via a scattering, diffuse scattering at the surface. But this would actually happen, and in some approaches, when surfaces are being modeled more carefully, we would add that kind of diffuse scattering term. And if I'm thinking of some kind of applications where this kind of math is actually being utilized, I'm thinking of a rendering of computer graphics landscapes. And there, of course, we know that in modern computer graphics, we have different kinds of materials. Some of them can be very, very glossy and glass-like and highly reflecting surfaces. For example, metals, they shine as a material in computer graphics. And there are other materials that do not shine. For example, like, leather couch or other things like this. And then they are objects that don't look shiny. And there, if you want to really model this kind of different behavior in the rendering engine, you actually have these kind of scattering parameters in description of light, so that not all light is being reflected nicely. So this is just to kind of point out to you that this is not the whole truth, and in fact, the things are generalized and utilized in everyday life in different kind of contexts. So that especially computer graphics would be the number one application here, or example, real world example, where the generalization is being made and utilized. And now the final slide, we basically conclude that we can now plot the reflectance R and the transmittance T, and we can plot it for two different scenarios. So for example, we can consider air glass interface. So this notation means that I'm coming with the ray of light from air and I'm hitting the air glass interface, and then the transmission goes into the glass. And then a second scenario would be that I consider the opposite case, so that I have a glass air interface with this meaning that I have the ray of light coming from glass, and then it's tries to transmit into the air. And this is the picture that shows me both the transmittance and the reflectance, so that the red curves are for the case of polarization that is perpendicular to the plane of incidence, and then the blue curves are for the case that I have the polarization that is parallel to the plane of incidence. And the dotted lines are the reflectance, and the solid lines are the transmittance for the interface. And I can see that when I'm at the close to a 0 theta I, so essentially I'm at the normal incidence, like the behavior is like this, so that the most of light is being transmitted. And at some point, the red curve just goes downwards, and in here I'm approaching the case where most of light actually is being reflected, as we can see from here. So we are approaching the grazing angles, where basically any dielectric interface acts as a reflecting mirror, reflecting surface. And then interestingly, I'm seeing here that the blue curve actually goes upwards. So it's not just illusion, it actually does go upwards. And in here, it's actually going higher to 1. So that something actually happens for that polarization component. And then say other possibility, glass-air interface. And now actually something seemingly magical happens, because I'm actually having this kind of trend that the curves approach 0 here, a little bit close to the theta I being close to 45 degrees. And here at the critical angle defined as a theta C, something strange seems to happen, which we call total internal reflection. And of course, that will be the main topic of next lecture, so I do not speak that much about it. But at least from kind of conceptually, what I can see that something strange happens near this critical angle theta C, and that's for the air glass scenario where the refractive index profile of glass has been taken to be 1.5. It's close to 42 degrees. And here we just say that total internal reflection of light starts occurring, which just means that essentially all of light is being reflected at this interface. And here, when we have an incidence angle that is larger than this critical angle, no light will escape in this reflection process, so that no light will be transmitted into air. But more on this on the next lecture, because it's actually something that we should pay more attention into it in terms of math, and also because it's quite important in terms of many applications. But more on that on the next lecture. So I stop here. I thank you for your time and patience, and enjoy the morning, the day, the evening, the night, and whatever time of the day. Thanks, bye-bye.